Okay, welcome to note set number 24. We're now going to continue our discussion of spectral analysis, primarily of sinusoids, but talk about how the DFT can actually help us deal with sinusoids in the presence of noise. So this is one of the most remarkable characteristics of the DFT, is that it can actually help us detect the presence of a sinusoid even when it's buried in noise so much so that when you look at it in the time domain, you can't even see a sinusoid, but yet you process it in the frequency domain and you can pull those spikes right up out of the noise. It's actually amazing, and it's one of the most touted characteristics of DSP processing. And if you have a firm understanding of this, you'll understand how a bunch of other things in signal processing can actually work, from things like matched filtering in communications and radar, to all sorts of different kinds of processing in electronic warfare and things like that. So anyway, let's get going on that. And there is no discussion of this in Preprocessing and Monolakis, so this is just in chapter 6 of Peratt's book. Okay, so here's the issue. We've got a sinusoid, but we're observing it in the presence of noise. So we're going to deal with a little bit of probability theory here. Nothing too outrageous, but you should be familiar with concept of a Gaussian random variable, and concept of correlation and variance. And things like that. If those are only vague notions to you, don't sweat it. We just want to get to the final answer here and see how to use it in the real world, rather than derive a bunch of probabilistic results here. So we're going to look at a simple scenario that, if you understand this scenario, it carries over to a lot of more complicated things. So we're going to look at a single complex sinusoid. So there it is. Has an amplitude of A, frequency of theta 0, and I put the phase at 0, and we could put a phase on it, but it doesn't really matter. And then added to that is each sample, V of n, is going to be what we call Gaussian complex white noise. So each one of those is like a random variable, with a Gaussian PDF, so bell-shaped kind of thing. It's complex valued, so really technically we would need to talk about a Gaussian PDF for the real part, a Gaussian PDF for the imaginary part, but let's not worry about that too much. We'll also assume that it's zero mean, so that means just, if we were to average this over all the possible values, or integrate this Gaussian PDF, it would end up, take the mean of the Gaussian PDF, it would be equal to 0. So the Gaussian PDFs are centered at 0. We'll say that it has a variance of sigma squared. Peratt, one of the things I don't like about his notation, I usually love his notation, but he uses gamma as variance, which I've never seen anybody else do. Everybody else just uses sigma squared as variance. So I'll use that in the notes. Variance will be sigma squared sub v, the v just telling us that it's the variance of this random variable v, which is our noise. And then the white part, white noise, that just means that from sample to sample to sample that it's uncorrelated. So again, I don't want to dwell on that too much, but it just means that if you were to observe the noise at one instant, there's no way you can use that to predict the value at the next instant, or any other instant for that matter. So we're going to be interested in something called the signal-to-noise ratio. It's the ratio of the signal power to the noise power. So if we look at this, you may be familiar with the power of a sinusoid being a squared over 2. That's a real valued sinusoid. For a complex sinusoid, it's just a squared. So that's the signal power. Notice that as the amplitude goes up, the power goes up. Doubling the amplitude quadruples the power. And then the noise power will be related, in fact not related, it is the variance. So that's just by definition of what variance means. So our signal power over our noise power will be a squared over sigma squared sub v. And we almost always want to express signal to noise ratio in terms of decibels, or dB. And since this is a power over power, we just do 10 log base 10. So we take the quantity, plug it directly in, take 10 log 10, and we get the result in dB. So we'll be talking about dB levels of signal to noise ratio. And so if we take the DTFT of this to just try to understand how things would work, we're going to take the DTFT of a finite amount of data. We've got this much data, and therefore what we would really be able to compute would be samples. Using the DFT, we'd be able to compute samples on this window DTFT. To avoid having to worry about, well, just where do the samples fall? How much zero padding are you going to use? We'll do all of our analysis in terms of the DTFT, keeping in mind as we go through this that we'll really be taking samples of this. But we can use zero padding to get that sampling as fine as we want, so it's really not an issue. So if I take the DTFT of each term, since the DTFT is linear transform, I'll get A times the window, and in this case, I haven't really said what window I'm using, so whatever window I'm using, and then I'll get the DTFT of the noise term, and I'm using a subscript W there to indicate that there's going to be some windowing effect on that. So I'm not going to show explicitly what the window does to that, at least not right here, but we'll just use the sub W there to indicate that we've used some window to do this. So we've got two terms, and if we plot each term individually, the red one over here would be the magnitude of this first term, and I'm showing you the main lobe centered at theta sub 0, which is the frequency of our sinusoid, and I guess I overdid it on the main lobe there. It's pretty wide. I guess I must be using a window that's really trying to push down the side lobes, but nah, I just drew it with PowerPoint. And then this term will just be some random thing, and because of the whiteness, white we said means uncorrelated from sample to sample, but what that also means, if you've studied random signal theory, that means that the spectrum, this DTFT, will be kind of flat across all frequencies. So that's what I'm showing here with the black thing. It wiggles some because it's erratic because we've collected some random data, but it's not going to have a large peak like the signal part has. So those are the two parts, but remember they get added together. So we can see that the peak of this will have some level, which will be A times some number P sub W. So obviously as A changes, so that P sub W will have to do, it's the peak of the window. So for a given P sub W, if A gets large, that peak will go up. If A gets small, that peak will go down. And so if A gets small enough, that peak can actually end up underneath the so-called noise floor, in which case we wouldn't be able to see the peak. Our goal is to try to figure out, for a given scenario, so for a given input SNR, how do we make sure that the peak pops up above the noise floor? What can we do? What are our tools? What are our levers that we can push to make this happen? That's our goal, is to understand that. And so let's go to the next slide. So we've alluded to a lot of the things on this slide already. This is what the noise does to us. We need that signal peak to pop up quite well above the noise floor. If it's only just barely above the noise floor, the noise floor may be erratic enough that we can't really see that there is, reliably see that there is a peak. So then we wouldn't even be able to detect the presence of this sinusoid. And that's one of our jobs, detect when we do have a sinusoid. Once we've detected and determined, yes, there is a sinusoid there, the next thing that we want to do is figure out where is that peak so we can estimate what the theta sub 0 is. There's lots of applications where we're trying to estimate the frequency of a received sinusoid. Communication applications have us doing that. Radar applications, sonar applications. So estimating the frequency of a received sinusoid in the presence of noise is kind of a bread and butter DSP process. But the noise may actually perturb where the peak location is. So when we pick off the peak location, it's not exactly where it would be in the absence of noise. And so we lose some accuracy in our frequency estimate. And the stronger the noise is relative to the height of the peak, the worse that frequency estimate will be. So in general, the idea is that we first try to detect the signal by looking for some significant peaks sticking up above the noise floor, and then try to estimate the frequency. And maybe even try to find out what was the amplitude of the sinusoid, and maybe also what was the phase. So in this set of notes and in this course, we're really only going to talk about the detection part of this problem. And if you're interested in the estimation part of it, it is covered in Peratt's book in chapter 6, so you will have access to that, but I'm not requiring you to read that at this point, but tuck it away, come back to it sometime. There are graduate level classes on something called estimation theory. We have one at Binghamton that I teach. It's called EECE522. And most graduate programs have such a course as well. So if you go somewhere else, you can probably pick that up there. Okay, so let's focus on signal detection, and in particular detecting a sinusoid in the presence of noise. And really we're trying to do this when the noise is so strong that if we were to look at the plot in the time domain, even with our well-trained human eyes and processing power of our brain between our ears, that's so good at picking out patterns and data that we can't even really see it. We look at the signal plus noise in the time domain, and it looks like could be just noise. We can't make out the sinusoid. So we will see that DFT processing will allow us to pull this peak up out of the noise floor. So to see how that works, we need to analyze the scenario so that we can figure out what is the relationship between the peak level for the signal and the noise floor height. And we will do all of this in terms of the DTFT because we're analyzing. That way we don't have to commit to a specific sample spacing, amount of zero padding, number of samples collected. We can just do everything in terms of the DTFT, and at the end say, well, okay, I've done enough zero padding so that my plot is actually pretty close to this DTFT and everything works just fine. So what are the parameters that determine how high I can pull the signal peak up above this noise floor? That's kind of the key question that we want to answer. And so let's look at that. So we take our received signal, which is the sinusoid plus noise, and we apply our window to it, whatever window we choose. We're not going to commit to a particular type of window. We'll just say a window. And then we take the DTFT of that. So we're going to pass this W through to both terms, and then pass the DTFT to both terms. And when we do that, we will then write out the expression for the DTFT of each of those terms. So if we write out the DTFT of the first term, so the window times the sinusoid, we get something that looks like this. The A is a constant, so we can pull that out in front. So really what we're doing is the theta sub 0 ends up combining with the complex exponential from the DTFT. So we can use a property of exponentials to write it like that. And so what we see is that we get this signal part, which is really like the DTFT of the window, but shifted by theta sub 0. And we've seen that already. We talked about that in the previous note set where we talked about, actually 2 note sets ago, I think we talked about how, a sinusoid, we take the DTFT of it, and it's the window kernel shifted by that frequency. So here's the signal part, and then we have the noise part, which is just the noise, which is random. So remember, think of those as just kind of every n we're rolling a Gaussian die to get a number. Not that there really is a Gaussian die, but you can think of it that way. Or for each n, we reach into a bag full of numbers and we pull a number out with a probability of getting a number driven by the Gaussian-shaped PDF. So we take each one of those numbers, weight it by the appropriate window, and take the DTFT of that. So we've got 2 different things that we need to analyze and understand. So we know that for our analysis, when we do the processing, we don't know this, but we're analyzing now. We're doing the thinking, the pre-implementation, pre-processing thinking to understand how things work. So let's say that we do know where the peak is. The peak of the signal part will be at theta equal to theta 0. So that's where the peak is. So let's focus on the peak. So evaluate theta at equal to theta sub 0. So when we plug that in, remember we had in here we had an e to the j theta minus theta sub 0, or maybe the other way around. And when we plug in theta sub 0 for theta, we get e to the j 0, which is 1, and so that's why that term is gone. And so what do we have? Just a sum of the window. And so the number A is going to get boosted by that number. And that, let's think about what that is. If we had a rectangular window, it's just a sum of n ones. So that number is n. And so we can immediately see that as we collect more data, if we were to process longer over a longer period of time, the longer we collect, the bigger this number will get. If we collect 10 samples, we'll have 10 times A. If we collect 100 samples, we'll have 100 times A. Aha! So collecting more samples pulls that peak up higher and higher and higher. Well, is that good? Well, it depends on what collecting more samples does to the noise floor. So we'll have to set this aside for now and come back and revisit this and say in just a little bit, well, I know that the peak is going up and up and up. What happens to the noise floor? I'll give you a hint. It's also going up and up and up. But guess what? We'll see that the signal peak is going up, 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 up faster than the noise floor is going up, up, up. Collecting more signal data will help us. That's always got to be a good thing, right? But we'll be able to see precisely how good it is and why it's good and what are the trade-offs. Okay, so we see that our peak height is getting boosted by the sum of the window. And we know that if it's a rectangular window, that sum is n. But what about for other windows? Remember, they are tapering off. They have a maximum height of 1 in the middle, and then they taper off down to 0 at the edges. So obviously, we're not going to get the total amount of n. So for these other windows that are tapered, this boost will be somewhat less. And so that's a price that we pay. We taper off to get the good side lobe characteristics, but we're paying a price in this noise processing. And so we characterize that with this thing called the coherent gain. And this is something that will carry through our analysis here. So it's the boost lost due to using a non-rectangular window. So we define it this way. We take a sum of whatever window we're really using divided by a sum of the rectangular window, which we know is equal to n. So it's the sum that we actually get compared to the sum that we would get if we used a rectangular window. So it's a relative measure. So if we were to really be using a rectangular window, we would end up with n over n, and the coherent gain would be 1. But when we use something other than a rectangular window, the numerator sum is going to be something less than n, and so our coherent gain will be less than 1. And so that's why we think of it as it's the boost lost due to a non-rectangular window. So it's a factor that allows us to adjust the n value that we would get with a rectangular window and reduce it by some factor. So maybe the coherent gain is not 1 but 0.9. So we'd be getting 90% of the boost that we could get if we used a rectangular window. Now, one cool thing about the coherent gain, you'd think that it would be dependent on the value of n. But it turns out that once you get up above a certain value of n, the coherent gain, since it's a ratio that involves two things that are going up with n, tends to level out and doesn't depend on n anymore. So we can talk about a coherent gain for a specific window type regardless of the length. So the hand window will have a coherent gain less than 1. The Hamming window will have a coherent gain less than 1. The rectangular window has a coherent gain equal to 1, and so on and so on and so on. So coherent gain is a parameter that we'll care about and we can use as a trade-off. Well, this window will give me this side lobe, this main lobe, and this coherent gain. So if you read that paper by Fred Harris that I pointed to in the previous set of notes and said this is a classic paper that if you're going to be a DSP expert, you have to have read and read and read and read. In that paper, Fred talks about coherent gain of windows and all that stuff. So it really is a comprehensive paper that kind of lays out all the details of this. And Peratt's book kind of chews that all up and spits it out in a little more coherent manner. Ha! Pun intended. All right, so let's move on to the next slide. So we can now rewrite our result. We had A times the sum of the window, and now remember our coherent gain was defined as the sum of the window divided by n. So if I take the sum of the window divided by n and multiply by n, the n's cancel and I'm left with the sum of the window, which is what we had there to begin with. So really all we're doing is we're breaking the sum of the window into two parts. One is the impact of the processing length, what I would get if I used a full rectangular window. So that's telling me how much boost am I getting from the fact that I'm using n samples, and then this discounts that based upon the window shape. So if I have a shape that's not rectangular, it's going to discount n from its full value to something less. Like I said, if the coherent gain is 0.9, it's going to cut my processing gain due to the processing length down to 90%. So if n is 1,000, it will look like I really was only using 900 points. I would get the boost that would be equivalent to using 900 points with a rectangular window. Okay, so we've got a handle on that first term, and we can see that the longer we collect data, the higher our peak will be. And so we can get a nice little characterization that the output peak height will be the input amplitude, that's A, times N, which is our processing length, times the coherent gain. So that's how you should think about it. Now, as I already alluded to, the output peak is going up, 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 but so is the noise floor. And so we need to look at a comparative measure. How does our output peak end up comparing to where the noise floor is? And so that's what we need to look at next. So we will define an output signal-to-noise ratio. We had an input SNR. Well, the output SNR will be the power of the peak. So we look at that height, and we're going to square it to get the power. And then we're going to look at the noise power at the location of the peak. So we're going to evaluate this thing at theta 0, and to get the power, we're going to take magnitude squared. So magnitude squared is the thing at theta 0 times its conjugate. Now, Peratt uses a bar for the conjugate symbol rather than using a star. So don't get freaked out over that, just different notation. It's one that's more common in the math fields than in engineering, and Peratt is highly mathematical, so no surprise there. But we're just going to take this thing times its conjugate, and that gives us the magnitude squared. And the reason that we do it that way is we know that that's a sum of two terms. This is a sum of two terms. So we have a sum of 2 times a sum of 2, and we'll FOIL that. So if you go all the way back to your high school days, you will remember that FOIL stands for first times first, outsides, so outside times outside, inside times inside, and last. And so those are our 4 terms that we'll get when we multiply A plus B times C plus D. Okay, so when we do that, the outside and the inside terms will end up giving us terms that can be combined together into a single term. So, so we've got this signal term out in front. That's the first times first. Then we've got the outsides times each other and the insides times each other. And if you work all that out and take advantage of complex conjugates and things, that's where this real part comes from. And then we get the last times the last, and we get something that looks like that. Now remember, the first involved only the signal part, so we end up getting a signal part. The last had only noise part in it, so that's purely noise. But the outside and the insides have both the signal stuff in it and the noise stuff in it. But that acts like noise because there is noise involved in it. So we really have one signal part and 2 different noise parts. And so we need to analyze those 2 noise parts separately. Okay, so we now have written out the power of the DFT power at the peak, and we see that it has part of it is a signal part and part of it is a noise part. So let's analyze those a little bit further. So we just wrote the noise. Well, we just wrote the power, but what we need to talk about is the average power, because this is all random. So we want to try to analyze this from the point of view of, on average, how will this look? Sometimes it'll be a little bit more than this, sometimes it'll be a little bit less than this, but on average, this is the value that we have. So it's sort of like going to a casino and trying to figure out, on average, how much would I win if I followed this scheme, or how much would I lose if I followed this scheme. So if we go back and we look at remember we said we had two noise terms. If we look at that first noise term and we take the expected value of it, that expected value can pass through all of that machinery, and it ends up snuggling up around the noise term, which we said was zero mean. So the expected value of the noise term ends up being equal to 0. And so that first noise term goes away. And the expected value of the first term for the signal, so the expected value of the signal term, well, there's nothing random in there. N is not random, A is not random, coherent gain is not random. So the expected value of 5 is 5. So the expected value of NaCg squared is NaCg squared. So that's done. And then the second noise term, we take the expected value out around this whole thing, but it passes through sums, it passes through the window, since those are not random, and finally snuggles in around the product of the noise terms. Now notice that it's Vn times V conjugate M. And when we do a product of two sums, we have to write them out with two different summation indices. Otherwise, when we do the product and we start manipulating products of sums into a nested sum, we'll get the wrong answer. So just remember, whenever you're multiplying one sum times another sum, write them out with two different indices so that you won't get confused on that. So that's how we get the N and the M, and one of those has a conjugate because it came from the conjugate term of that. So that's what we got. And, you know, without going into the details, we're waving our hands a fair amount because this course is not about random analysis, but we're going to just, you know, we have to hit a little bit of that as we go here, but we're not going into all the details. So we're taking the correlation of Vn at relative to Vm, and it turns out, if you know the theory of white noise, and if you don't, it doesn't really matter, just trust me, that turns out to be a delta function with the variance of the noise out in front. So we get sigma squared V out in front of a delta function, which is delta of n minus m. So notice that we're summing a double sum over this. So let's think about the inner sum. When we're letting m run over its value, whenever m hits whatever the value of n is, we select that term. So this is a sifting property. And when we use this property, it converts this double sum down into a single sum. And so when we do that, we end up getting this single sum here, where this W sub m gets converted to a Wn, and that's how we get the square there. So again, don't stress out over this. Just, you know, accept that this is how it works if you're not up to speed on all of this kind of manipulation. So we now see our fundamental result. We've got the average power of our DTFT having one part due to the signal and one part due to the noise. And so we can compare those two things. This is the signal's peak power in the DTFT domain, and this is the noise power at where the peak is. So if we compare those, this is the thing that we'd like to make much bigger than this. So the bigger our signal peak power is relative to the noise power at the peak, the better we'll be able to see that peak. And so we will look at the ratio of these two things. That will be our output signal-to-noise ratio. So here's our output signal-to-noise ratio. Here's the signal power term that we just came up with. Here's the noise power term that we just came up with. And now we're just going to do some algebraic manipulation of that to get it into a form that makes sense. So the first thing we're going to do is we see the A there and we see the sigma squared V. We'll pull those out in front and put a box around them and say, aha, that's the input SNR. And then the next thing we're going to do is we've got an N with a square. So we're going to take one of those and we're going to pull it out in front also. So we've got our SNR, input SNR. We've got one of these N's which we'll pull out. And there's a reason that we're manipulating this way. And so we end up with N times SNRI. And then we have something in brackets, which we will call PG, or processing gain. So this quantity here is N times the coherent gain squared divided by the sum of the window values squared. Remember, the coherent gain involved a sum of the window values. Now we're talking about a sum of the window values squared. And so if we look at this processing gain, I've just rewritten what we had up here. And now I've subbed in for coherent gain here. And we're squaring the coherent gain, so we have that there. And so notice what ends up happening here. We can think of our processing gain. If we clear out some of these n's here, we've got a 1 over n squared. So let me pull that 1 over n squared out. 1 will cancel with that, and 1 will go down in the bottom. So there's the 1 that I put down in the bottom. And so look what I have here. I have the sum of the window values squared divided by n times the sum of the square of the window values. And that's the processing gain. So don't worry too much about, well, what does that mean? We'll interpret what this processing gain does for us. This box here is just so that you can kind of see that it involves the window, and it involves it summing it and then squaring it and then summing it. So what we've done is we've got a nice little result here. Notice that the processing gain is just a characteristic of the window, and in particular the window shape. So what do we have here? And also notice that if we have a rectangular window, this is going to end up being n squared, and 1 squared is still 1, so that'll be n times n, which is n squared. So for a rectangular window, we'll have n squared over n squared, which is 1. So for a rectangular window, the processing gain is 1. And for other window shapes, guess what? Less than 1. So look what we have now. We've manipulated this into a nice form that we can think about. Our output SNR, the thing that we care about, the larger we make that output SNR, the better we're able to actually detect this peak. If the SNR is too low, we won't be able to reliably detect the peak. If it's high enough, we'll be able to reliably detect the peak. And we've written that output SNR in terms of a product of 3 things. The SNR that we start at, which could be really, really small. So remember we were talking about in the time domain, the sinusoid being completely buried in the noise, indistinguishable looking at the time domain record. That might be a case where the noise is actually stronger than the signal power. That would mean a negative SNR in dB form, or a fractional SNR in non-dB form. So these are all in fractional, or in non-dB form. So we start off with something really, really small, much less than 1 perhaps, maybe 0.1, which would be minus 10 dB. So we might start off with SNR being 0.1, and then we're multiplying it by n here. That's the effect of our processing length. Don't count what you zero pad out to. So it's not your FFT length. It's the actual amount of data that you collect. You collect 100 turns, 100 samples, but you zero pad out to 1,000. N is not 1,000. n is 100. But now we've got a 0.1 for a minus 10 dB input SNR. So 0.1 times 100, we're now up to 10, which is a plus 10 dB. And our processing gain, depending upon the window type, its shape, might be close to 1. So that might knock us down a little bit more. But we can see that this is the workhorse right here. And then this is a small price, a tax that we pay due to the window shape, which we may have picked because we're trying to address side lobe issues or something like that. So we've got the three effects here, but it's really the N times the SNR in that is the main workhorse. So, and remember, when we have a rectangular window, processing gain is 1. So as a rough first cut, most signal processing people don't even think about the processing gain. They just say, okay, what's my output SNR? Well, I got 0.1 input SNR, non-dB, times N, which is 100, so I'm up to 10. My output SNR is 10 non-dB or 10 dB. Now, also, keep in mind that this is a product, and remember when we take dB, we're taking logarithm. Logarithm of a product ends up being a sum. So that's the beauty of this. Each of these terms, once converted into dB, we could write out in dB form. So it would be N converted into dB. So all these things are contributing to a SNR, which is a power ratio. So we treat N as a power. We treat processing gain as a power. We treat SNR in as a power. So to convert N into dB form, we would take 10 log 10 of N. So if N is 100, we take 10 log 10 of 100. Log 10 of 100 is 2. So N of 100 is 20 dB in dB form, plus processing gain in dB form. So if processing gain is 1, because we're using a rectangular window, dB of 1 would be 0. And then plus SNR in dB. So maybe SNR in is minus 10 dB. So we've got minus 10 dB plus 0 dB plus 20 dB, and we're up to 10 dB. Same thing that we got thinking here, 0.1 times 1 times 100. Okay? So it's this dB form with summation that the real engineers think about. But we derive it in the non-dB form. It comes out of the math. But when we use it, when we think about it, we think about it in the dB form. So if there's one thing you glean from this little chart here, it's that one of the advantages to working in dB is that we can often results spec'd in terms of dB are done adding things. That's why filter frequency responses are done in terms of dB, because if we see that it says 0 dB, we know that it doesn't change the level. If we see frequency responses at 10 dB, we know that it's going to raise the signal's dB level by 10 dB. So working in dB is a very convenient way of doing things. All right, slide. So let's just talk about our, what we've seen here and how we put it into practice. So this is a general rough rule of thumb, just very rough. You're usually aiming to get an output SNR of about 14 dB or better, so that you can reliably see a peak well above the noise floor. Processing gain is less than or equal to 1. Rectangular window, the only one with a processing gain of 1. All other tapered windows have a processing gain less than 1. So if you're aiming to get good side lobes, and you're using a tapered window, Hanning, Ham, I did it backwards, Hamming, Bartlett, Kaiser, Blackman, any of those, you're going to pay with a reduction of processing gain. Coherent gain versus processing gain. Processing gain comes into play when we're talking about how the output SNR gets changed. So it accounts for effects on both the signal peak as well as the noise floor. Whereas coherent gain really only tells us about a change to the signal peak amplitude. So if you remember, I told you it's a race between, they're both going up. The signal peak height goes up as we increase the processing length, but so does the noise floor. Well, the coherent gain only tells us how the peak level goes up. It does go up, but the processing gain tells us how, what happens with the race between them. So that's the distinction. And as I said, we usually specify these coherent gains and processing gains in terms of dB so that we can convert all of these equations instead of into a product of three terms. We have a sum of three terms, each one being in dB. Notice that the coherent gain, when we do dB on that, we have to square it first because it's not a power. It's something that is operating directly on A, so it's a ratio of amplitudes. So we would have to square it first, or equivalently take that square out in front and make the 10 into a 20. So we do 20 log 10. So if we're taking a dB form of this equation for the peak level, it would be 20 log 10 of n plus 20 log 10 of the coherent gain plus 20 log 10 of the amplitude, and that will give us the peak level in dB. Then if we want to do dB analysis of SNR, we would do 10 log 10 because those are all powers. So now n here is operating as a power gain, whereas here it's operating as an amplitude gain. So here we do 10 log 10 of n plus 10 log 10 of processing gain plus 10 log 10 of the input SNR. So make sure you keep that straight. Probably one of the most common errors that people make. Okay, slide 11. Let's just take some alternate view here. Try to get a feeling for how this all works. So we had this equation earlier for our output SNR. So this is the equation, same thing that we were just talking about, just written out explicitly. We've got the n and the a up in the numerator. We've got the coherent gain, and we're squaring all that to get it into a power form. And then down in the bottom, we've got the variance of the noise times the sum of the square of the window values. And for this analysis here, let's just talk about a rectangular window. So the coherent gain will be 1. The sum of the squares of the window will be n. And so we can just rewrite, for this case, we now have n squared a squared over n times the variance. And so now look what's happening here. We can now interpret what we've got. So if we look at what's happening in the numerator, we've got our signal power is a squared. That's the power of a complex sinusoid. And that's getting boosted by n squared. So that's getting boosted by n times the coherent gain squared. Coherent gain is equal to 1 for the rectangular window case. And what happens to the noise power? The input noise power gets only boosted by n. And so that's how we end up coming out ahead. Input noise power, the the input signal power gets boosted by n squared to become the output or peak signal power, and the input noise power only gets boosted by n to become the noise the noise floor power. So that's how the race gets won by the signal. So that's why, even though they're both going up as n increases, the signal power in the DTFT result goes up faster, goes up as n squared. And so that's how we end up, these things cancel out to give us an n. So we have our output noise, our output signal to noise ratio is n times the input signal to noise ratio. And remember, this was for processing gain equal to 1 for a rectangular window. So this is our rough rule of thumb. Ignoring any losses due to a non-rectangular window, this is the best we can do from an output SNR point of view. So you tell me, oh, I've got minus 10 dB SNR. I can use this thinking. I need to get up to 14 dB to be able to be reliably detected. So I need to go from, let's say we even want to be, a little excessive, and I need to get up to 20 dB. So I start at minus 10 dB. I need to get up to 20. I need an improvement of 30 dB. So I need my n value in dB form to be 30. Well, undBing 30 dB with 10 log 10 means I need an n of 1,000. So rough rule of thumb, if I need to go from minus 10 dB input to 20 dB at my peak, output SNR, I need a processing length of 1,000. So I need to collect at least 1,000 samples to get that. And I'll probably need a little bit more if I'm going to use something other than a rectangular window. So that's how DSP engineer thinks about these things. This is the key rule of thumb. And if you work around people who are doing this, they're just tossing this little rule of thumb off just like that over and over and over. Input SNR, output SNR, I need 10,000 samples. And that's how they're doing. Now, then they'll adjust it for when they do get around to deciding which type of window they're going to use. So, big, key result. Yet another view. Why does it work this way? This is what I like to do is, I don't want to just throw the bare equations at you. I like to look at it and see, why? What makes it work this way? And of course, it always ends up with some yellow boxes on my slides when we get down to why does it work. Well, let's look at what we got going here. So here's our DTFT evaluated at the peak point. So what's really happening? So when I plug in theta sub 0 for theta, notice that this thing, which was a complex sinusoid, at other frequencies when I'm doing this sum, I'm adding up complex numbers that are just kind of wiggling all over at different frequencies, different angles as I go through n. But when I let theta be equal to theta sub 0, what happens? Well, this complex exponential becomes e to the j 0, and it goes away. It becomes 1. So that's gone. And so look at that. I'm just adding up a 1, so that's gone. I'm just adding up my positive numbers for my window. Windows are always positive numbers just because of the nature of them. And this kind of shows why that needs to be the case. And so I'm adding up a bunch of purely positive real numbers and multiplying that number by a. So I can think of I'm adding up a bunch of vectors on a complex plane that all lie on the real axis. So they're all perfectly lining up. And those of us who are in the DSP field, we say what we're doing is this first sum, the signal part of this, at the correct frequency is adding coherently. They are in phase with each other in phase, in phase, in phase, in phase. And look, the more of them I add together, the longer they are. And what is the effect of tapering? Well, some of these, the first one, the ones towards the beginning of the sum and the ones towards the end of the sum are going to be smaller than 1. So my total length will shrink due to the shaping of the window. So I have a reduction in that part of my processing gain. Okay, good. What happens to the other term? Even at the correct signal frequency, notice that when I plug in theta equal to theta 0, I still end up getting something here that's a complex number that's just going to be, as I let n go, that thing's going to be cycling around at different at different angles, and it's going to get hit by random complex numbers, which will perturb it randomly to even other angles and lengths, and also tapered by the window. So each one of the terms in this sum, second sum is just going to, so each one of these things for each value of n is just some random vector kind of pointing off into anywhere with random lengths and random angles. And I add those all up. And so they mostly kind of cancel each other. They are going to grow. As I add more of them, I'm likely to get a vector with a longer length, and that will be the magnitude of the noise floor. So that does grow, but it grows incoherently because all these vectors are just kind of ad hoc, randomly floating all over the place. And so they don't add coherently, they add incoherently. So this idea of something adding coherently, all lined up on a complex plane, versus adding incoherently, not lined up on a complex plane, that's a big, big idea. Shows up all over the place. Matched filter processing for communications, matched filter processing for radar, matched filter processing for sonar, all sorts of other things, biometric detections, facial recognitions, all sorts of stuff like that. So it's a big, big, big idea. And it explains why adding more numbers to our DFT processing gives us an improvement, because this will grow fast. This will grow, but not nearly as fast because it's summing incoherently. All right, let's go to the slide. So we've done all of this analysis in terms of the DTFT. We've not given any thought to the fact that we'll actually be computing all of this on a grid. So down here I'm showing that what we'll really be calculating are points on this underlying DTFT. So what I'm showing here is ignoring the noise part of it and just showing the signal part of it. And we've been counting on getting this high of a peak. But what happens if the peak lies between two of my grid points? I don't get the full height. I'm going to lose some amount. And that's the worst case right there, when the peak lies exactly in the middle of two of my grid points. And so we can actually compute for a given window how much you would lose in that worst case scenario. Sometimes you might get lucky. Your peak might lie on a grid point. Sometimes you will not get lucky. You'll get as unlucky as you could be, and the peak will lie halfway between the grid points. So if you're trying to make sure your processing will always give you enough output SNR to achieve your goal, you want to make sure that under the worst case scenario, you'll meet that. So we used a worst case analysis. And this is something that's usually captured through a kind of further discounted coherent gain. And so if you look in Fred Harris's paper, he talks a lot about this aspect. So what we do is when we capture our coherent gain, we offset, we put in an e to the j 1/2 delta theta. So that's accounting for the fact that we would be halfway between two grid points. Now that delta theta is impacted by zero padding. So that is the spacing between the FFT computed frequencies. So as I zero pad, that will get smaller and smaller and smaller, and that will make this term closer and closer to being a 1. So if we do a heavy zero padding, the impact on the worst case accounting for the impact on the coherent gain is actually fairly slim. So this really has the biggest impact when we're not doing a lot of zero padding. So anyway, just something to keep in mind as you look in papers, and particularly if you ever go off and read Fred Harris's paper. If I think about it, I'll try to post a copy of that paper to Blackboard, so you'll have it. If I forget, send me an email and remind me. Okay, so that's it for this set of notes, and I'll see you in the next one.